Hello everyone. Today, I'll present my research titled Digital Microwave Characterization of Ice-Accreted Power Transmission Conductors for SAR-Based Monitoring. My talk will cover summary, introduction, methodology, data analysis, and conclusions. Let's start with the summary of this research. To summarize upfront, we use microwave radar for iced transmission line monitoring, analyze radar echo characteristics to reveal ice thickness inversion principles, and verify via ISAR imaging, identifying ice surface mirror reflection, and via ice penetration diffraction. This work delivers both theoretical and experimental support for radar-based ice thickness monitoring. Grid ice disasters common in high-altitude and low-latitude areas severely threaten power system, safety, and stability. Icing adds extra mechanical loads to conductors and towers, triggering breakages or collapses, causing billions in losses and outages. It also leads to conductor galloping and short circuits from uneven de-icing. Traditional model-based prediction methods are low-cost but inaccurate due to terrain and microclimate interference. Radar satellites, however, offer all-time, all-weather, wide swath monitoring. Ice layers alter conductor dielectric properties and geometry, changing backscattering characteristics. Current research lacks systematic analysis of conductor icing electromagnetic interactions. We address this using a microwave anechoic chamber for high-precision scattering measurements. Our methodology starts with the experimental platform, a 24 x 24 x 17 meters microwave anechoic chamber that shields electromagnetic interference for a pure test environment. Its 1 GHz 18 GHz RF system has 100 decibels dynamic range and is less than 60 dBsm sensitivity for precise scattering data collection. The orbital coordinate system has its origin at the antenna orbit semicircle center, 0.5 meters above ground, 9.3 meters antenna aperture, x-axis opposite the door, z-axis upward. We used a 1.5 meters, 38 millimeters diameter, 500 kilovolts ACSR conductor mounted 1 meter from the turntable axis perpendicular to the antenna, iced via a 1 meter long, 178 millimeters inner diameter PVC tube, 48 hours, freezing. The RF system, TEX, RX antennas, VNA computer, enables precise control and echo acquisition parameters, 118 GHz, 30 degrees incidence, plus or minus 22 degrees turntable rotation, 0.05 degree step, 0.05 GHz frequency step, 8 cm range resolution, 5-minute imaging. For calibration, we measured iced conductor echo, then empty chamber echo to subtract noise and support only scattering characteristics. Vector subtraction removed noise, and substitution method with known RCS calibration bodies. Metal balls plates ensured precise RCS calibration. Polarization calibration matrix operations eliminated system errors, yielding calibrated matrix S. HH VV echoes are similar RCS, -5 to 10 dBsm, but frequency domain data lacks structural info. Fourier transform of 1/6 GHz HH echoes generated 1D profiles, 3 low-frequency peaks plus ice penetration scattering and 2 high-frequency peaks. Peaks 1-218.2 cm and 2-317.5 cm. Peak 2 strongest equals conductor echo. Peaks 1 and 3 equals ice layer echoes. ISAR imaging BP algorithm validated peak positions. Conductor scattering comes from ice penetration diffraction. With inner-outer ice mirror reflection, distance difference enables high-accuracy ice thickness inversion. In data analysis, we obtained 1D range profiles of known ice thickness conductors and inferred ice thickness via echo peak distances. ISAR imaging confirmed our ice thickness inferences. 70 mm iced line echoes include ice surface signals, ice penetration diffraction, and mirror reflection from the opposite ice surface. This work provides a radar echo-based inversion method and fills the gap in conductor icing electromagnetic interaction analysis. Our results confirm experimental reliability. The temperature-controlled 1333 degrees Celsius anechoic chamber and 5-minute measurements prevented ice changes, with the RF system ensuring data accuracy. Polarization correction. 16-term error matrix solution yielded matrix S. Reflecting true scattering characteristics. See Figure 7 to 9 for corrected echoes and 1D range distribution. Key results. HH divided by VV echoes are similar. RCS, negative 5 to 10 dB. ISAR validated 3 echo peaks. Conductor scattering equals ice penetration diffraction. Inner-outer ice mirror reflection is confirmed. Core conclusion. Distance difference-based ice thickness inversion is highly accurate. This research explores the microwave scattering mechanism, provides a technical reference for SAR-based all-weather monitoring, and strengthens power grid safety in extreme weather. That's all for my presentation. Thank you for listening. I'm happy to take questions.